You board an airplane, perhaps settling in for a long journey. You gaze out the small, oval window. What do you observe down below? Likely, clouds like fluffy cotton, or maybe a patchwork quilt of fields and towns. The horizon stretches far and wide. It appears remarkably, undeniably flat. A straight line dividing earth and sky. This experience is universal for air travelers. It's a powerful, very convincing illusion. This perception often leads to a simple question. If the Earth is truly a sphere, a giant ball, why does my flight path seem so straight? Why don't pilots constantly steer downwards? To avoid flying off into space, surely. It's a perfectly reasonable question, one that touches upon physics. It involves perception and our place in the cosmos. The answer is wonderfully elegant. It reveals how science works. We live our lives on a very small patch, a tiny fraction of Earth's total surface. Our immediate surroundings always appear flat. Think about your local park or street. Does it curve noticeably? Probably not. This everyday experience shapes our intuition. So, when we ascend to 35,000 feet, our brains tend to extrapolate this flatness. Even though we know intellectually Earth is round, the sensation of straight flight persists. But the universe is under no obligation to make sense to our limited human senses. The reality of flight is far more fascinating than a simple straight line over a flat plane. Aircraft are indeed following the Earth's curvature. They do it constantly, seamlessly, and precisely. This essay will explore just how they achieve this. We will delve into the science and the technology that makes it all possible. Prepare for a journey of understanding. The Earth is not just round. It is an oblate spheroid, to be precise, slightly squashed at the poles and bulging a bit at the equator. This is due to its rotation, a cosmic ballet of gravity and centrifugal force. But for most practical purposes, like flight, we can think of it as a near-perfect sphere, a very, very large sphere indeed. Its circumference is about 40,075 kilometers, or roughly 24,901 miles. That's a truly colossal scale. Now imagine trying to see this curve from an airplane at cruising altitude. Typically, this is around 10 to 12 kilometers, or about 6 to 7.5 miles up. This might sound very high, and it is, relative to our ground-based experience. But compare it to the Earth's vast diameter, which is about 12,742 kilometers. Your altitude is a mere sliver, a tiny fraction of the planet's overall size. It's like an ant standing on a giant beach ball. From this vantage point, the visible horizon is limited. It stretches out for a few hundred miles. Over such a distance, the Earth's curvature is subtle, very, very subtle. It amounts to only a few degrees of arc. Too gentle for our unaided eyes to detect reliably. You would need specialized instruments, or a much higher vantage point, like that of an astronaut in orbit, to truly appreciate the majestic curve of our world. Then it becomes undeniable. So, the lack of a perceived curve from your airplane window is not evidence of a flat Earth. Far from it, my friends. It is simply a consequence of scale, the sheer immensity of our planet, compared to our relatively low altitude of flight. The curvature is there, always present, gently guiding your aircraft, even if your eyes cannot fully grasp it. Science allows us to see beyond our senses. It reveals the true nature of things. Our human perception is a remarkable tool. It evolved to help us survive. In our immediate environment, here on the ground, we are adept at judging distances on a human scale, navigating our local neighborhoods, catching a ball, or avoiding obstacles. These are tasks our senses handle well. Our brains are wired for this terrestrial existence, this familiar, relatively flat world. We are creatures of the surface. However, when we venture into realms that operate on vastly different scales, such as the altitude of a cruising jetliner, or the immense distances of outer space, our intuition can sometimes lead us astray. The rules of perception change. What seems straight or flat locally can be part of a much larger curve globally. Our senses are not inherently equipped to process these cosmic dimensions accurately without the aid of reason and scientific understanding. Consider looking at a large circle from very close up. If you are small enough and close enough, a tiny segment of that circle's edge will appear almost indistinguishable from a straight line. This is precisely what happens in an airplane. You're looking at a small segment of the Earth's enormous circumference. Your field of view is limited. The subtle drop of the horizon is too minuscule to register as a definite curve. Your brain defaults to its familiar, flat interpretation. This doesn't mean our senses are faulty. They are simply optimized for a different context. The illusion of flat flight is a testament to the Earth's grand scale, not a denial of it. It's a beautiful interplay between our biology and the physics of the universe we inhabit. Science provides the corrective lens, allowing us to understand phenomena that extend beyond our everyday sensory experience. It bridges the gap between perception and reality. So, if the Earth is curved, what keeps planes stuck to it? Why don't they fly off into the cold indifference of space? The answer, my friends, is a fundamental force, one that governs the cosmos from the fall of an apple to the dance of galaxies. That force is gravity. Earth's gravity constantly pulls everything towards its center. This includes you, me, and every single airplane that graces our skies. An aircraft in flight is in a delicate balance between several forces. Lift, generated by its wings, counters its weight. Thrust, from its engines, overcomes air resistance, or drag. But it is gravity that dictates the down direction. As the plane moves forward, gravity continuously pulls it towards the Earth's center. This constant pull ensures the aircraft naturally follows the planet's curvature. It's not about the pilot actively steering down. It's an inherent part of flying within a gravitational field. Imagine throwing a ball horizontally. It doesn't travel in a straight line forever. Gravity pulls it downwards, creating an arc. Now, imagine throwing that ball incredibly fast. So fast that as it falls, the Earth's surface curves away beneath it at the same rate. This is the basic principle of an orbit. An airplane isn't moving fast enough to orbit, not by a long shot, but the principle of following the curve due to gravity is fundamentally the same, just on a smaller scale. Therefore, level flight for an airplane doesn't mean flying in a geometrically straight line in three-dimensional space. It means maintaining a constant altitude above the Earth's curved surface. The aircraft's instruments are calibrated for this. They define level relative to the local gravitational pull. So, by maintaining level flight, the plane is, in fact, tracing a path. That perfectly mirrors the Earth's roundness. Gravity is the silent, ever-present co-pilot. The shortest path. Navigating by great circles. When you want to travel between 2 points on a flat map, the shortest distance is a straight line. Simple enough, right? But our Earth is not flat. It is a sphere. So, what is the shortest path between two cities on a globe? It's not what you might intuitively draw on a typical Mercator projection map. Those familiar rectangular maps distort reality, especially near the poles. They make Greenland look enormous. The true shortest path between 2 points on the surface of a sphere is called a great circle route. Imagine slicing the Earth in half, straight through its center, and also through your departure and arrival cities. The edge of that slice on the surface, that is a great circle. Any circle drawn on the surface of a sphere whose center coincides with the center of the sphere is a great circle. These are the straight lines of spherical geometry. Airlines are very interested in efficiency. Less fuel means lower costs, and shorter flight times mean happier passengers. Therefore, for long-distance flights, pilots navigate along great circle routes whenever practical and permitted by air traffic control. On a flat map, these routes often appear curved, sometimes arching far to the north or far to the south. This is an artifact of the map projection, but on a globe, you'd see it's the most direct way. So the path your plane takes is not just following the Earth's general curvature. It's often following a very specific, mathematically determined curve, the Great Circle. This is a more sophisticated understanding of what straight flight means on a round planet. It's about optimizing the journey within the constraints of our spherical home. The universe often presents us with elegant solutions if we know where and how to look. Modern marvels of aircraft navigation. How does an airplane precisely follow these invisible curves, especially great circle routes high above the Earth? It's not done by eyesight alone, that's for sure. Pilots rely on a symphony of advanced technologies. Sophisticated navigation systems are constantly at work. These systems know the Earth is a sphere. They perform their calculations accordingly. They are the unsung heroes of modern aviation, ensuring safety and efficiency. One of the cornerstones is the Inertial Navigation System, INS, or its more modern cousin, the Inertial Reference System, IRS. These amazing devices use gyroscopes and accelerometers to continuously track an aircraft's position, its orientation, and its velocity without needing any external references. Once initialized with a starting position, they can feel every turn, every acceleration, every subtle change in direction, maintaining incredible accuracy. They inherently account for the Earth's shape. Then, of course, there's the Global Positioning System, GPS, a network of satellites orbiting Earth, transmitting precise timing signals. An aircraft's GPS receiver picks up these signals from multiple satellites simultaneously. By calculating the time differences, it can pinpoint its location anywhere on the globe with remarkable precision, often within meters. GPS data constantly updates the flight management system, confirming and refining the path along the curve. These systems, often working together, feed information into the aircraft's flight management system, FMS. The FMS is like the brain of the operation. It contains vast databases of routes and navigation aids. Pilots program the intended flight path, a great circle, into the FMS before takeoff. The FMS then provides guidance to the autopilot or the human pilot, ensuring the aircraft adheres to that curved trajectory. It's a marvel of engineering. In the pilot's seat. Trusting instruments. Over instinct. Imagine you are a pilot, cruising at 37,000 feet over the dark ocean. No visual landmarks are visible below. Your senses might scream that you are flying straight and level in a flat, featureless void. But your instruments tell a different story. They indicate your precise position on a spherical Earth. They show the programmed Great Circle route, a gentle, continuous arc towards your destination. What do you trust? Your ancient instincts or modern science? Pilots undergo rigorous training to understand and trust their instruments implicitly. This is a core principle of aviation safety, especially when flying in conditions where visual reference to the ground is lost, such as at night or in clouds. This is known as Instrument Flight Rules, or IFR. Human senses can be misleading in the air. Spatial disorientation is a real danger. Instruments provide objective, reliable data about the aircraft's state and path. The aircraft's attitude indicator, for example, shows the plane's orientation relative to the Earth's horizon, even if the real horizon is not visible or appears flat. This instrument is gyroscopically stabilized. It always knows which way is down towards Earth's center. By keeping the symbolic aircraft level on this display, the pilot ensures they are following Earth's curvature, maintaining a constant altitude above its surface. It's a constant, subtle adjustment. So, while the pilot isn't consciously steering down to follow the curve in a dramatic fashion, they are constantly making minute corrections based on instrument readings, or the autopilot is doing so under their supervision to maintain the programmed flight path. This path is inherently curved due to gravity and optimized as a great circle route. Trust in technology and scientific principles overcomes the limitations of human perception, ensuring a safe and efficient journey. And remember, if your instincts ever tell you to fly straight into a mountain, trust your instruments instead. Redefining straight flight paths in 3 dimensions. What does flying straight truly mean? In our everyday language, on the ground, straight implies a line that doesn't bend or curve, a ruler's edge, perhaps. But when we move into 3-dimensional space and consider a journey over a spherical planet, the concept needs a little refinement, a little cosmic perspective, if you will. Is a plane flying straight if it maintains a constant compass heading? Not necessarily over long distances. If a pilot tried to fly a constant compass heading, say due east for thousands of miles, they would not trace a great circle unless they started on the equator. Instead, they would fly a path called a rhumb line or a loxodrome. This line crosses all meridians of longitude at the same angle. On a Mercator map, a rhumb line appears straight, but on a globe, it's a spiral. That eventually leads to one of the poles. It's not the shortest distance. True straight flight, in the sense of the shortest path over a sphere, is the Great Circle, as we've discussed, and level flight means maintaining constant altitude above the Earth's mean sea level. This inherently means following the Earth's curvature. So, an aircraft flying a Great Circle route at a constant altitude is, in a very real sense, flying the straightest and most level path possible in that 3-dimensional gravitational context. The language we use can sometimes obscure the underlying physical reality. The flight feels straight to passengers because their local frame of reference inside the cabin is not accelerating dramatically up or down or side to side. The changes in direction are so gradual over such vast distances that they are imperceptible without instruments. The plane is indeed flying a straight path, the straightest path possible on a curved surface, guided by gravity's gentle hand. The elusive arc. Why the horizon hides Earth's bend. Let's revisit why we don't see that curve, even from 35,000 feet. We've touched on Earth's immense size, but there are other factors at play. One is the nature of our vision. Human eyes are good at detecting sharp contrasts and distinct lines. The Earth's curvature, from typical flight altitudes, presents itself as an incredibly subtle, gradual change across a very wide field of view. It's not a sharp, defined arc. Atmospheric conditions also play a significant role. Haze, dust, and water vapor in the air can reduce visibility and obscure distant details. The horizon itself is often not a crisp line, but a somewhat fuzzy transition zone. This atmospheric scattering of light can further soften any perception of curvature, making it even harder for our eyes to pick up on the gentle declination of the Earth's limb against the sky. Moreover, to truly perceive the curve, you need a very wide, unobstructed field of view. An airplane window offers a relatively narrow portal. Your brain tries to make sense of this limited input, often flattening the scene by default. You'd need a panoramic vista, like that afforded to U-2 spy plane pilots, or passengers on supersonic Concorde when it flew. or ideally, astronauts in orbit, to really see the distinct roundness without ambiguity. So the absence of a visible curve is not a failure of physics, nor is it evidence against a spherical Earth. It's a combination of factors: Earth's massive scale, our limited altitude, the physiology of human vision, the constraints of an airplane window, and the obscuring effects of the atmosphere. The curve is there, undeniably. Science and mathematics confirm it. Our technology allows us to navigate it, even if our eyes alone cannot always appreciate its full glory. Science, technology, and the wonder of curved flight. So, there you have it. The next time you are soaring through the sky and you gaze out at that seemingly flat horizon, remember the hidden complexities, the elegant science at play. Airplanes appear to fly straight because in a very real sense, they are. They are following the straightest possible path across a majestically curved surface, our home, planet Earth. It's a dance between physics and ingenious engineering. Gravity is the constant, guiding hand, gently pulling the aircraft towards Earth's center, ensuring it hugs the planetary contour. Advanced navigation systems, like INS and GPS, provide the precise information needed to chart these curved courses, often great circles, optimizing for distance and fuel. Pilots trust these instruments over their sometimes deceptive senses to maintain safe and efficient flight along these invisible highways in the sky. It's a triumph of human ingenuity. The illusion of flat flight is a powerful one, born from our everyday experience and the sheer scale of our world. But science allows us to peer beyond illusions, to understand the deeper truths of the cosmos. The Earth is a sphere, and our aircraft navigate its roundness with grace. This understanding doesn't diminish the wonder of flight. If anything, it enhances it, revealing the intricate knowledge and technology that makes modern air travel possible. So, sit back, relax, and enjoy your flight. You are participating in a remarkable feat, a testament to our comprehension of the universe. You are smoothly, almost imperceptibly, arcing across the globe, following a path shaped by gravity and charted by the stars of human intellect. The world is round, and thanks to science, we can navigate it as if it were, well, almost straight, the straightest kind of straight there is, on a beautiful blue sphere. Don't just fly straight. Subscribe and join the Curvature Club. Hit that like button, and let's keep soaring together.